Hi, welcome to lesson 1.3. We're going to solve equations with variables on both sides. By the end of this, I want you to be able to explain how to solve an equation with variables on both sides. We'll look at a bunch of different ways to do that. Determine whether an equation has one solution, no solution, or infinitely many solutions. And then use equations with variables on both sides to model and solve real-life problems. All right, so one solution problems, that's what you've been working with all along here. You solve, you get variable equals a number. X equals -1/2, x equals 32, whatever I happen to throw out at you. Then you've got the new scenarios, no solution, where the variables eliminate, like the x's are gone, the y's are gone, whatever they are, they're gone. And the equality that's left is not true. You get something like 0 equals -6 or something like that. I don't know, it's whatever it is. Infinitely many solutions, on the other hand, variables eliminate, but this time you're left with an equality that is true, okay? 0 equals 0, 4 equals 4. And you may even notice as you're solving identical expressions on either side of the equal sign. If you notice that, like you get a 2x minus 4 on each side or a half y minus 72 on both sides, well, you know what's going to happen then. Everything's going to cancel out and you're going to have 0 equals 0. You can even stop as early partway through the problem and say, well, this is going to be infinitely many solutions. Or you can keep trying to solve till you get down to the variables gone and then you say, oh, the equality is true. Still, infinitely many solutions. All right, so when we're solving equations with variables on both sides, our ultimate goal and our process really remains the same. Our goal is still to get the variable by itself on one side of the equation, if at all possible. And we use inverse operations and keeping our equation balanced, doing what we do to one side, do to the other side, like I said, to keep everything balanced as our process. All right, so let's take a look here. We're going to solve equations. R equals -5r plus 18. Now, as a general rule of thumb, I like to keep my variables positive, my variable terms positive if possible. So if it makes sense, I'm going to move my -5r over here with the other r. Then it gets it over on one side, and it's going to make it positive because I'm going to add 5r to both sides. Now remember, there's a little 1 there, so what's 1r plus 5r? Sorry, 6r. And then we're going to divide both sides by 6, and r equals 3. Kind of feel like a pirate right now saying r so much. Okay, so we moved our variable term over. It's our goal, get our variables together, combine like terms. Sometimes you combine like terms by moving things on the other side of the equal sign. All right, over here, example B, 6 times the quantity 1 plus half x equals 2 times the quantity x plus 1. I see parentheses, I see numbers outside of them, I think I better distribute. So 6 times 1 and 6 times a half. So that's 6 plus 6 times a half is 3x. So 6 plus 3x equals, multiply 2 to both things, 2x plus 2. All right, now we want to get variables on one side, constants on the other. Now, as you get better at this, I'm moving the 2x over first, so I've got 6 plus x equals 2. You'll get to the point where you can move the constant and the variable terms at the same time. Now I'm going to subtract 6 from both sides. X equals -4. Okay, now let's take a look down here. 3x minus 5 equals 7 plus 3x. Let's move our variable terms over. I'm going to subtract 3x from both sides. Well, that seems kind of odd. Where am I moving it to? What's happening? Oh no! The variables terms have disappeared. But -5 does not equal 7. That means we have a no solution, and that's all you can write. Our remaining statement is not true, so we say no solution. We can't say that x equals anything because x has gone bye-bye. All right, and you can kind of see that maybe even as we start and go, well, I have a 3x and a 3x. Here I'm subtracting 5. Here 7's positive and being added. So it's probably not going to be equal. So you can use a little intuitive thinking there if you want, and if you're starting to see that. The better you get at this, the more you'll notice those things. All right, let's look over here. 1/4 times the quantity 8x minus 12 equals 2x minus 3. All right, well, we better distribute. 1/4 times 8, that's 2x. 1/4 times 12 is 3, so 2x minus 3 equals 2x minus 3. Deja vu? Oh, see what I meant when I said you're going to have two terms, or two expressions that are the same on either side of the equal sign? What do you think's going to happen? 2x, if I subtract 2x from both sides, they're gone. But I'm left with -3 equals -3. I now have infinitely many solutions because it's really the same expression. They are equivalent to each other. Infinitely many solutions. Now, you could have stopped right when you got to 2x minus 3 on both sides and said, oh, it's infinitely many because you know they're identical. Great, then just say that. That is perfectly fine. If you want to try and make the variables eliminate, go for it. If that just makes sense, keep solving until you can't solve anymore, then just do that. Okay, so you have the legs of a right triangle that are supposed to be the same length. What's the area of the right triangle? Well, here's our triangle. One side length is represented as 3x, the other is 2.5 minus 2x. Now, why would we be doing this? Maybe we got to figure out, what's the area of this space because we're going to get dirt for a garden, sod it in, I don't know, but you might have a right triangle and you need to figure that out. So now we're going to have to figure out first, what is x, then the area, because if we just start plugging stuff into the area equation, we don't know what x is, we don't know what the actual side length is yet. So it says they're the same length, so let's create an equation. 3x is equal to 2.5 minus 2x. Okay? Get variables all on one side. I'm going to add 2x to both sides. 5x equals 2.5. Okay, mixed numbers a problem. Let's turn it into an improper fraction. So 5x equals 5 halves. All right, so now we have multiplication, we divide, but if I divide by 5, dividing by 5 is the same as multiplying by the reciprocal, right? Reciprocal of 5 is 1/5, so I multiply by 1/5. Keep that order in mind, it's a second number. So 5's cancel, x, and you do a little cross canceling. So we have x equals 1/2. Now, that doesn't mean the side length is 1/2, that just means we can plug in, and our side lengths, they better become the same when we plug them in. So we're going to do 3 times 1/2, which is 3 halves. I'm going to keep it improper because we know we're going to have to multiply and stuff later. We need improper fractions for that. I'm going to make this 5 halves minus 2 times 1/2, which is, well, 2 times the order of operations. Do that first. 2 times 1/2 is 1, right? 5 halves minus 1, which we could rewrite as 2/2, is 3/2. Oh, good. They match. Now, could we have just figured out one and gone on with it? Yes, but it's always good to double check that we get the same length, that we know that we solved correctly. If for some reason we didn't, then we might need to go back and check our work. Now, how do we find area? Area of a triangle is base times height divided by 2, or 1/2 times base times height. And our base and height have to form a right angle. Good news, they do. All right, this is the time where 1/2 times base times height probably makes a little more sense because we're dealing with fractions, right? So our area is 1/2 times 3 halves times 3 halves. All right, multiply. 1 times 3 times 3 is 9. 2 times 2 times 2 is 8. 9/8, which is really 1 1/8. Do they give us units? Nope. Square units for our area. So now, hopefully you can solve equations with variables on both sides. Know when you're going to have one solution, no solutions, or infinitely many solutions, and can start to apply them to other problems. It's not just an equation to solve, but it's an equation to solve within the context of something else. Thanks for watching.